Okay, we're ready to begin the webinar, and I think it's a good idea to get started just by letting you know a little bit about Gary Prentice, who's our National Sales Manager, and will be doing the webinar. Gary's a great person to be doing this webinar. He has 39 years of experience handling measurement and control applications, and much of that time has been spent with temperature-related activities. He actually started out solving measurement and control problems in steel mills in Pittsburgh, and the rest of his career, as I mentioned, has a lot of temperature-related background. So without anything else from me, here's Gary.
Thank you, Richard. When I'm involved in a seminar on temperature, I'll often start by asking the question if anybody needs to measure temperature accurately. And as you might imagine, the responses are all over the map. But there's one common answer that I hear repeatedly, and that is no. Plus and minus 1 degree is fine. And that's actually a helpful response to me because it gives me direction on where I have to go with the seminar. It tells me that this particular group really doesn't appreciate how hard it is to measure temperature to that degree of accuracy. Plus or minus 1 degree in the process environment is, in fact, a high accuracy measurement. And you really have to do everything right if you're going to get an achievement of that degree of accuracy. If you look at your own processes, there are certain temperature loops where you know for sure you need to work on accuracy. Then there's going to be a whole bunch of temperature measurements where you're really only looking for trends, so accuracy is not so important. And then there's going to be some number of loops in between there, and where you're on the fence, not knowing if you need to implement some accuracy techniques or not. For those measurements with uncertainty, what I would recommend you do is ask yourself the question, do I need to calibrate these loops? Do I need to verify these loops? Are they part of a PM schedule? Because if the answer is yes, it means that you have some amount of drift in those loops. And what happens is many of the techniques we employ to achieve accuracy also prevents drift. So by selecting the right sensor, it reduces drift. By selecting the right measuring device, we reduce drift. By using 4-wire RTDs, we reduce drift. So if we can reduce drift for you, then we're pushing out the frequency of your calibrations, and that's going to help with operating expenses. So accuracy, drift reduction, operating expenses can be all interrelated. So what I want to cover today in this session is several areas. One, take a look at selecting the right sensor for the application to achieve better accuracy. To look at ways we can eliminate error caused by the external environment. How do we reduce error contributed by lead wire? And then, is there anything we can do at the measurement level to reduce error? So let's start by just a simple application where we're trying to measure the uniformity of the product in this vessel, the temperature uniformity of this product. And the operations folk have said we need plus or minus 4 degrees of temperature uniformity at an operating temperature of 250 Fahrenheit. We're going to use 2 sensors to help us measure whether or not we're getting that uniformity. If we choose type J thermocouples, because that happens to be one of our plant standards, we may not be able to achieve our goal. We're going to see in a minute, one of the temperature standards we use in the U.S. tells us that a type J thermocouple is only accurate to plus or minus 4 degrees at 250 Fahrenheit. So with two type J thermocouples and a product that is perfectly uniform in temperature, the two sensors could be disagreeing by as much as 8 degrees. So at that point, you've got choices. You can calibrate out this error. You can begin a PM program so that the two sensors stay in sync, or perhaps you want to consider changing the sensor. And an option for a sensor to change to would be a Class A 100 ohm platinum RTD. At 250 Fahrenheit, that sensor is accurate to 0.7 Fahrenheit. So with two sensors and perfectly uniform product, those two sensors could possibly disagree by less than 1.5 degrees, which is certainly way better than the 8 degrees of difference we could have seen with the two type J's. So you're going to see as we go through this session, I'm very prejudiced in favor of RTDs for a lot of reasons, all of which are accuracy and drift related. By selecting the best sensor, you're gonna make huge gains in measurement accuracy. And as far as I'm concerned, if the process temperature allows, I'll always reach for an RTD. I referred to standards we use in the U.S., and this is one of them. I know full well that there are many temperature measurements we have to make that are outside the realm of RTDs, so we need thermocouples. If you look at some of the options with thermocouples, look at the column marked 300 degrees Fahrenheit. And look down to see the accuracy of a J and a K thermocouple at 300 Fahrenheit. This ASTM standard is showing those thermocouples to be plus or minus 4 degrees Fahrenheit. If that's not sufficient for your application, then there's an option. We can use premium grade thermocouples, or what may otherwise be called special tolerance thermocouples. And basically, these thermocouples are made up from wire that has a higher level of alloy purity. And if you look at that same column for 300 degrees Fahrenheit, you'll see a premium grade J or K is accurate to plus or minus 2 degrees F. So we've cut our error in half. If we moved on to considering an RTD, a Class A RTD, I've done the calculations for you at 300 Fahrenheit to keep everything on par. The Class A RTD is accurate to 0.8 Fahrenheit. So these three slides, if you look at the progression, we could loosely say that if you transition from standard grade thermocouples to premium grade thermocouples, you cut your error in half. If you transition from premium grade thermocouples to Class A 100 ohm platinum RTDs, you cut your error in half again. So sensor selection is, again, very important in your overall measurement accuracy strategy. Now let's look at extension wire, lead wire. We all have thermocouples that get direct wired back to PLCs and DCSs. And for those applications, we need to use thermocouple extension wire. And unfortunately, thermocouple extension wire is yet another source of measurement error. Look at the column marked standard error. If you're using a standard extension wire for J or K thermocouple, that extension wire is adding another plus or minus 4 degrees Fahrenheit of error. That's on top of the thermocouple error. If that's unsatisfactory, just like with the thermocouples, we do have a choice. The column off to the far right says special error. There is a special tolerance extension wire we could use that cuts the extension wire in error in half. So that's an improvement. But keep in mind that the error shown assumes that this extension wire is, call it like new condition. It has not been contaminated by typical industrial atmospheric contaminants. As the wire purity, the alloy purity gets contaminated, this error just grows larger. If you overstress the wire by exceeding its temperature limits in one direction or the other, the error contribution to by the wire is increased. So when it comes to measurement accuracy, thermocouple extension wire is not our friend. How many of you even try to measure how much air is being caused by your extension wire? I don't know anybody that does that. Typically, they ignore the whole subject until operations says, I don't believe this temperature anymore, or there's catastrophic failure. We all know thermocouples fail, but thermocouple extension wire also fails. And when it fails, it has to be replaced. If you replace it in kind, you're just reintroducing the errors that extension wire contributes to the measurement. So replacing failed extension wire with more extension wire just perpetuates the problems. So I'm a big proponent of getting rid of extension wire. And so what are the choices? What other technology is available to us to avoid or minimize the use of extension wire? It's temperature transmitters, it's remote I/O. Both of these types of solutions send their signals back to the DCSs and PLCs using copper wire. Copper wire, you can expect, will last the length of the life of your plant, which is not true of the thermocouple extension wire. So at least there's benefit. Once you put the copper wire in place, you likely are never going to have to replace it. Modern I/O products have the same performance characteristics of transmitters today. And with many of these direct wired sensors, their data acquisition points, you don't want to invest a transmitter on each and every one. Remote I/O is a very affordable alternative. And again, it gets rid of that extension wire. You will have a short section of extension wire between your thermocouple and the transmitter or I/O. And because it's short, you're not going to break the bank if you use premium grade thermocouple wire and keep that error to a minimum. If you have not studied the effect of extension wire on an RTD sensor, you may be lulled into thinking that there is no error because we use copper wire for bringing RTDs back to the receiving device. But that's not true at all. The copper wire we use for RTDs is in fact resistance. RTD measurements are resistance. So if not handled properly, the lead wire we use for RTDs can contribute significant error to an RTD. The one way around it is to use 4-wire RTDs, and that eliminates all of the lead wire error. And let me build up, telling you the story about building up to using 4-wire RTDs. In the microprocessor-based world, RTD measurements all start with constant current sources. And the job of the constant current source is to generate the excitation current that's going to be fed through the RTD. Then we measure the voltage drop across the RTD. We use Ohm's law to calculate resistance. And then we apply the resistance to the RTD curve and read out the value in either degrees C or degrees Fahrenheit. So that's what everybody does today in making an RTD measurement. Well, when the industry first started using 2-wire RTDs, we realized immediately that this is not a very accurate measurement because, in fact, what we're measuring is the sum of the lead wire resistances, represented here by R1 and R4, plus the RTD. And if you have long lead wires and R1 and R4 are significant, the error can be significant. So very early on, then, we went to 3-wire RTDs. And the trick to making sense of 3-wire RTDs, we've added the 3rd wire out to the RTD, but here I've colored that lead in red because I'm signifying that that lead is only internally tied to our high impedance voltmeters, if you will. And with it being high impedance, there is no current flow through the red lead. There's no current flow through R2. There is no voltage drop across R2. So anything that goes on with that 3rd lead can be totally ignored. So how do we make the measurement in a 3-wire measuring circuit? Well, first we measure the voltage shown as V1. And that delivers us the value of lead wire resistance R1. And then we measure the voltage at V2. And that gives us the sum of the RTD plus lead wire resistance R4. And then we subtract the two. And over on the left, you can see the subtraction. If R1 and R4 is equal, they drop out of the equation and we're left solely with the value of the RTD. And if all that is true, then this is a very high accuracy measurement. And then Murphy's law gets involved, and Murphy guarantees that R1 and R4 are never going to be equal. And it's things we can't control, things like wire intolerances, gauge intolerances, work hardening of the wire as we pulled it. Assuming there's no installation errors, perhaps the biggest contributor to R1 and R4 never being equal is corrosion. Corrosion that changes the diameter of the wire and therefore the resistance. So when R4 and R1 don't equal one another, what are the results? Well, if we're using a 100-ohm platinum RTD and we have as little as 1 ohm of imbalance, we've just introduced over 4.5 degrees Fahrenheit of error in the measurement. And here we are trying to measure to plus or minus 1 degree accuracy and 1 ohm has given us 4.5 degrees of air. So you can spend your life calibrating this out or move on to a 4-wire RTD, which of course is my recommendation. And with the 4-wire RTD measurement, note that we have 2 leads that are colored in red. Those are tied to the voltmeter inside the receiving device. And that voltmeter, if you will, is high impedance, which means there is no current flowing through those red leads. That means the lead wire resistance R2 and R3 don't enter into the equations at all because there's no current flow, no voltage drop. So now our voltage is measuring exclusively the RTD. Unlike the 3-wire, we're not measuring R1, we're not measuring R4. We don't have to subtract the 2, and therefore we can never ever get an imbalance. So all that error that we saw due to resistance imbalance no longer exists. So with a 4-wire RTD, you can have lead wire of any length. It can be varying in resistance constantly, and yet we have no error. The only thing you perhaps might have to consider is to make sure that the total resistance doesn't exceed the drive capacity of your constant current source. But with 4,000 ohms of drive capacity, it's virtually impossible to overburden that constant current source. In my travels, about the only objection to using 4-wire RTDs that does make sense is if you have legacy input cards on perhaps a PLC that can't make 4-wire RTD measurements. They can only make 3-wire RTD measurements. So in those cases, perhaps it's time to retire that generation technology. Or, if for whatever reason 4-wire RTDs are not in your future, I want you to consider this trick. Upgrade your 100 ohm platinum RTDs with 1,000 ohm RTDs. We have the same error chart that we saw earlier, where for a 100 ohm platinum RTD, 1 ohm of imbalance causes a 4.5 degree error. If we substitute a 1,000 ohm RTD for that same 100 ohm platinum RTD, and we still have 1 ohm of imbalance, the error is reduced by 1/10. So expressed in terms of percent of span in that chart, if we were dealing with 0 to 300 and using 100 ohm platinum, that 1 ohm of imbalance would give us a 1.6% error, which is quite significant. Replace it with 1,000 ohm RTD, and that 1 ohm of imbalance gives us an error of 0.16%, which is way more tolerable. We all have VFDs, motors, radios, noise sources of all types. If you're running thermocouples and RTD direct wired back to the DCS or PLC, then you got to remember you're transmitting long distances, very low millivolt level signals. Those low level millivolt signals are susceptible to distortion from this noise if you can't keep the noise off the lines. So This is a reminder, really, to use best practices to keep that noise off of your signals. For reasons I can't explain, we do a great job of protecting 4 to 20 milliamp signal wires, but sometimes we forget the temperature signal wires. So use drain wires, use proper grounding, use physical separation to keep noise off those low-level signals. Or another approach is to change those low-level signals to a high-level signals as close to the sensor as you can. Because a high-level signal is not affected as greatly as the low-level signals with the same amount of noise. So signals like 4 to 20 milliamps and HART protocol and RS-485 typically handle normal plant noise much more successfully than low-level millivolt signals. Another form of external air sources is represented in these photographs. There are times when we head down a path of convenience and we end up creating temperature measurement errors. In both of these photos, we have solid sheath sensors that extend from the thermal well out into ambient conditions. And Murphy is pretty much going to guarantee that the ambient temperature is going to be way different than our process temperature. So what happens? Well, there's a wicking effect. The solid sheath that's out in ambient is wicking temperature away from your process hot junction. Or as shown in this particular sketch, it's just the opposite. The ambient temperature is very hot. The process is very cold. So heat flows from ambient down the metal sheath down into the process well, and it creates offset errors. And if it doesn't create an offset error at a very minimum, it's going to produce an extensively long time delay in your measurement response. And the solution is very simple. The solution is to just change the configuration of your sensor such that the solid sheath is totally embedded in the thermal well, and the solid sheath does not extend past the well out into ambient conditions. So this is an example of where we're, again, eliminating errors caused by ambient conditions. At the measuring device, the receiving device, if you were to buy remote I/O or transmitters from any of the big instrument companies, I think you're going to find that there are quite similar performance characteristics from one vendor to another. But if you were going to try to differentiate, this probably would be the list of specifications that you would study, comparing one product against another. And just to comment on a few of these, input resolution, you want that to be as high as possible, because the higher the input resolution means the smaller the change in the sensor temperature that can be detected. With long-term drift specifications, you want very low drift long-term, so that you can eliminate your receiving device as part of the error long-term and push out your calibrations. RTD excitation current, you want that to be low, because the lower the excitation current, the less self-heating effect error you get in the RTD measurement. And for RTDs and both RTDs and thermocouples, the voltage portion of the measurement, you want that to be a very high impedance voltage measurement so that you don't draw any current. Advanced diagnostics might be useful in helping you predict future failings of a sensor, either due to excessive corrosion or other characteristics. If you're chasing the absolute accuracy, then you've bought the very best sensor you can afford, or very best sensor for the application. And even though it's the very best, there's still some minute error in that RTD. And if you're looking for the very best in accuracy, you can't ignore that final bit of error in the RTD. You got to get rid of it. And there's a couple of techniques that we use to get rid of that. Bath calibration or calendar Van Dusen are both lend themselves to eliminating that final bit of error and giving you the ultimate in results. If you're using remote I/O or transmitters, those types of devices make your temperature measurement and digitize the value. If you then choose to send that temperature signal back to the DCS or PLC via 4 to 20, that decision has just created 2 more errors in your measurement. It's already digital in the field at the transmitter or I/O. To turn it into 4 to 20 milliamps, you have a D to A conversion error. And then back at the DCS, we have to convert the analog signal back to digital, which has a analog to digital conversion error. So I really recommend that once the temperature is digital, keep it digital all the way back to the control system and avoid those conversion errors. Using HARP protocol is one technology to allow you to keep it digital, or you can use Modbus serial or Modbus over Ethernet or other ways to keep it digital. Earlier we saw that transmitters and I/O helped eliminate error by eliminating thermocouple extension wire, which is an error source. We saw that transmitters and remote I/O is a tool we could use to eliminate error caused by noise on our lines. And now we're using transmitters and I/O to eliminate analog conversion error. So we have a common theme. Let me just summarize what I tried to communicate. These are what I believe to be practical steps that any of us can take to improve the temperature measurement accuracy. These same steps also improve the stability of your measurement and minimizes then your calibration frequencies and cost. Use 4-wire RTDs whenever the process temperature permits you to do so. That eliminates all the error caused by lead wire. I also recommend that you use Class A RTDs whenever possible. The price differential is insignificant, and it's a market improvement in accuracy. If your process temperature requires the use of thermocouples, then use premium grade thermocouples and use premium grade extension wire. Be sure when you're direct wiring sensors back long distances, be sure you implement noise protection strategies to keep EMI and RFI off of those low-level signals. Better yet, get rid of thermocouple extension wire and use transmitters and remote I/O to digitize everything, transport everything over copper wire, transport via high-level signals, and avoid many of the issues that we discussed. Avoid ambient air caused by extending your solid sheath sensor out into ambient conditions. Get rid of your final RTD offset air by implementing bath calibration techniques. By the highest accuracy, the most stable measuring system you can afford, whether it be transmitters or I/O. And once you have this temperature signal digital, keep it digital back to the control system. With that, I say thank you for listening and open the floor to questions that you may have.
Thanks, Gary. That was very informative. So let's, again, if you have any questions that came up, either things that Gary mentioned in this webinar or just any other temperature questions that you might have that weren't delivered through this, certainly feel free. Now is a perfect time to send them over to us. You can go, there's a QA button as part of our panel. It's on the right corner, or it's also in the right side panel. Just go there and send it to us. You can also send it to us on chat. That would work as well. So any questions that came up from this, feel free to
Peter, bear with me, I'm reading this. Peter asks, what temperature do you think is too hot for RTDs? Okay, so try to keep this as concise as possible. If you're using thin film RTDs, I'm comfortable in those going to 800 Fahrenheit, maybe 850 Fahrenheit. After that, we found that wire wound sensors handle higher temperatures with greater accuracy and stability. So moving to wire wound, I'm comfortable getting up to 1,000, 1,100 Fahrenheit. There are techniques we can use to get still higher, but we got to look at those very carefully because there's other conditions that get in the way. But, you know, this also brings to mind that I strongly suggest you, when you're dealing with temperature, tell your vendor what temperature you're operating at, because then they can take a look at what it is you're buying or want to buy, compare it to your operating temperature, and give them an opportunity to make recommendations to give you, you know, the solution that is most stable, most accurate. Eric says, how do you recommend connecting thermocouples to thermocouple extension wire? I'm not sure if this is a loaded question or not. I've seen a lot of wire nuts in my day. I don't recommend wire nuts. I'm a believer in terminal blocks, and better yet, I like it when the thermocouple wire and the extension wire are sharing the same hole in the terminal block, so they are in direct contact with one another. So that would be my recommendation. Cheryl says, you recommend mounting I/O or transmitters close to the sensors, but what if you have a hot process? Okay, so yeah, good point. Any of these transmitters, I/O products have ambient temperature limits, typically, maybe upwards of 185 Fahrenheit, 85 C, that type of thing. If you don't want to get them so close to your process that you're going to exceed their ambient temperature. So now you're dealing with more of the mechanical design of the temperature assembly, where you're going to use extensions of some form to bring the electronics away from the conducted and radiated heat of your process. We have some graphics. We've done some computer simulations here, and there's a whale of a lot of variables here. So I'm not giving you a straight answer because of all these variables. It's the type of material you're using, the temperature you're starting at, whether you're using a 1-inch process connection or a 1/2-inch process connection. So all of these impact how long the extension has to be to make sure that you don't over temperature your electronics. What have we got? How do I help prevent drift in RTDs? Well, Class A, the Class A sensor is one that I recommended, and typically these are the more precise, the higher accuracy sensors, 0.04, 0.06 type sensors. And these sensors have been aged or temperature cycled. They're aged from 0 to 1,600. JR, my buddy next door, he's giving me some help here. 600. 0 to 600. We temperature cycle those sensors for 1,000 hours. So that basically anneals or ages those sensors and goes a long way in eliminating the rest of that drift.